Today I will talk about the power EP. It is called power exponential expectation propagation. It's short for power EP. Before I talk about the power EP, I will quickly review at what kind of conditions we will use the expectation propagation algorithm, the EP algorithm, and what is EP algorithm, and at what kind of condition the EP will intractable, and we will result to the power EP algorithm. So usually we are interested to find unknown parameters or latent variables in a model, and according to the Bayes' theorem, we will corresponding to calculate the posterior distribution of the unknown parameter. So the posterior distribution Px given y is observations, is equal to the prior distribution Px times the likelihood function Py given x, and the P model evidence of Py. To calculate the posterior distribution, and for the first condition, if we're given a bunch of the ID observations, so suppose we give a number of the observations, the likelihood function Py given x is equal to the product of Pyi given xi to n number. And if the Py given xi is a more than one term distribution, suppose it has a total d-term distribution. So the likelihood function will total be d2n terms. So at this time, we cannot directly to calculate posterior distribution directly. And another condition, we cannot calculate the posterior distribution is the model evidence Py x. This integral cannot help the closed form solution. So when one of the conditions occurs, we cannot get the analytical solutions for the posterior distribution. At this time, we need to resort to some approximation method. And for the approximation method, today we only talk about the EP algorithm.
So n is number of observation or?
N number of the ID observations.
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 Okay.
So now I write for the EP algorithm. Now I write the posterior distribution as Px is equal to the product of P of x. It's equal to the product of factors. I use PA to represent each factor. And EP algorithm just want to find a posterior approximation Q of x, which is very close to the posterior distribution P of x, and both of them are in the exponential families. So how to find the approximations Q of x? EP mainly works to minimize the KL divergence. P of x, Q of x, Q of x, and we can write it as a projection P of x. And it also shows that the KL divergence between Px and the Qx is corresponding to it's to matching the sufficient statistics between the posterior distribution P of x and the Q of x. So we want to find the approximation Q of x is equal to project P of x to satisfy the equation G y Px here GI is represent the features of the exponential families. So in terms of the Gaussian distribution, the features is x and x squared. So matching the sufficient statistics in context of the Gaussian distribution, we just want to calculate the mean and the variance of the posterior distribution P of x, and using a Gaussian distribution Q of x with that same mean and variance. So this
what's the projection?
the KR divergence is corresponding to find to matching the sufficient statistic and sufficient statistic of P of x and Q of x. If I said in context of Gaussian distribution, we just find the mean of px, variance of the px, and the Q of x is a Gaussian distribution, which had the mean and the variance calculated from this distribution. So
I want to know what sort of projection mean.
you mean
If I will use the
you mean the KR?
yeah.
I just use the projection P of x to represent the KR divergence. You just change the it's the same meaning.
You call the KL as a projection.
Yeah, the KL divergence P of x, Q of x to represent projection of P of x. If I given an input P of x, the projection means that I will calculate the KL divergence and I will get a Q of x.
I guess you want to say the projection is the Q of x that minimize the KL divergence, right?
Yeah, minimize KL divergence. Then find the Q of x.
This is the two slash is all.
It's not or, I don't know what here the meaning, but I know it's just a separate this true posterior distribution, this approximations. Here I don't
We
know
can
what
just
the meaning
define.
of the.
Maybe define the KL.
You mean the definition?
Yeah. Yeah. You mean what is the KL?
What's the meaning of the two?
Use the symbol.
Okay, write down the definition of KL divergence.
KL divergence.
I guess you probably want to use another marker.
KL divergence.
Okay. Maybe. Okay. KL P Q PX. This definition of the KL divergence. Then I will minimize the KL divergence in context of the Gaussian distribution. Minimize KL divergence. I will
don't
take
think
the
this is the
derivative.
definition of KL divergence. That without the second term. The second term is you just put a constraint there. You're trying to minimize that, but you add the constraint just to make sure. But the KL divergence definition doesn't have the second term.
Without the second term.
Yeah.
Add the second term just to make sure that this can be used on normalized distributions, right?
I guess because you do the minimization and you want to have the Qx is constrained to be a distribution, then you definitely add the second terms there, because and probably you can put a lambda there just as a Lagrange multiplier or something like that. Okay, I'm just guessing, but definitely the KL divergence doesn't have that.
This KL divergence has been talked about in the previous presentations. So today I just want to review. So yeah.
Okay,
I did not get the, did not do,
It's okay.
yeah,
Yeah.
to review the detail. I forgot it.
Excuse me. What's the usage of the Power EP? Is the same as the EP?
Yeah, same as it's Minka.
Okay, and what's the advantage of that? Is
I will talk about that. Yeah. Since I will first review what's EP.
okay.
Yeah.
After that, you just
Yeah, I will talk about what. Yeah, it has some constraint and it will use the power EP.
Okay.
So after I review the EP algorithm, I will just drag the EP process. Yeah, here. Yeah. Since EP want to find the approximation Q of X, and according to the matching the sufficient statistics, and since P of X equals to the product of the factors TA of X, and if we can find approximation for each term, then we multiply all of these approximation terms. We also can get a good approximations as Q of X. So EP works just to approximate, just to one approximation for each term. Here we use TA tilde to represent the approximation for each term, TA. So for the EP process, we will first initialize all the approximations of the term. And the Q of X is equal to the product TA of X. And then, since the EP want to find each approximation for each term, so for each term, TA of X, we will first remove the term TA tilde of X from the approximations Q of X. So we use Q naught A to represent the rest of the distributions except this term. And then we want to update this term. So we want to, now we're using the project of TA of X, Q naught A of X. Right? The T of A, right, is a true distribution of the, is a true value, true function of the T of A. And this part is also the approximation from this equation. So now we can get the Q of X new. So this is an updated approximation according to this projection. So then so we're using the updated approximation Q new of X divided Q naught A of X. We get the updated approximation TA tilde new of X, right? So this is the, then we will repeat and actually iteratively to do this process for each term, and until convert, we will get the approximations of Q new of X. This is approximations of P of X. So this is the basic EP process. But just now I mentioned that in the standard BP algorithm, the main component part is the projection part. The projection is just to compute just to matching the sufficient statistics between the P of X and the Q of X. So in the projection part, here I also consider in context of the Gaussian distribution. So for the projection and the Gaussian distribution, we need to first calculate the Z equal to TA of x q naught a of x dx. This is a normalization factor. Then how about the first moment and the mean of the Gaussian? The mean is equal to TA of a normalization factor and TA of x q naught a of x dx. And also for variance is equal to 1 over j TA of x q naught a of x squared dx minus mean squared. If we can have the closed form solution for all of these integrals, then this EP can work very well. But sometimes for some factor TA of x, it can be any function, right? So at sometimes the integrals cannot have closed form solution. For example, suppose we have a P of x, the posterior distribution is equal to 1 over x squared plus 1. Okay, equal to TA. Suppose it only has two terms. It's okay? TA or TB. TAX and TBX. And equal to 1 over x squared plus 1. And the TB, for simply, I also bracket 1 plus 1. And now we want to update the term TA of x. So in the projection part, we need to calculate the integral of 1 over x squared plus 1 and the q naught a x dx. In terms of Gaussian, suppose we also suppose that we use a Gaussian approximation to approximate the p of x. But we know that this integral is not easy to evaluate. But we know that the x squared plus 1 q a naught of x is easy to evaluate, right? So the power EP algorithm just to approximate the p of x only using the easier integrals. So now I can write it. Suppose TA of x q naught a dx, right? Actually, we should have we should do the integral like this, but it's not easy to evaluate. The power EP just to approximate the posterior distribution using the easier integral at this form. So they just add a component on the factor T of x, and in that case, here the beta is equal to -1, right? Actually, in power EP algorithm, the parameter beta can be any value you desire and you want. And in the following, I will talk about the detail of how the power EP works. In order to give what's this?
Yeah, in your example, I can find the q naught a.
Yeah. In this example, the q naught a is this part. Sorry. No, not this part. No. Sorry, it's not this part. Initially, we have the approximate. Suppose for each factor we have suppose it's Gaussian distribution, EA tutor, and then Q is a product of all the factors. So if we use a Gaussian distribution, then Qx is a Gaussian distribution, right? And the Q naught a for the term TA of x, Q naught a is a Gaussian distribution, divide the Gaussian distribution, so Q naught a is still a Gaussian distribution.
Okay, you mean that the TA or something like
Yeah,
that?
here is
yeah.
the T2.
Yeah, T2 is the is related to the TA.
No, TA is
Just for the Gaussian.
approximation, initialize approximation.
Okay.
Initialize you can set any value. You can set it a normal distribution.
It's not dependent on the TA.
I think the posterior T is a true and posterior Gaussian distribution trial. Think about it. Let's think about the Bernoulli distribution and we support this Gaussian distribution. Yeah, yeah, actually it depends on the T of A. No, I cannot find it. Yeah, I'm not very clear about it, but yeah.
In initialization, you for example assume some Gaussian distribution for the TA tutor,
Yeah.
and after that try to find out the Q of X, and
Q of X.
Yeah,
Yeah.
exactly.
yeah,
All of this is
and
initial.
the Q not A is also a Gaussian distribution.
Yeah, still Gaussian
Yeah.
distribution.
And when you wanna, for example, run the EP on this one, the term of the Q not A, I think it must be, for example, related to some Gaussian distribution.
Yeah. If you want to Gaussian distribution as approximation, then this part is Gaussian distribution. And
And you use, for example, Gaussian distribution because for example, finding the closed form of the integral is easier. And
you mean why I choose a Gaussian distribution?
yeah,
You choose what kind of distribution depends on your problems. You want to find a approximate distribution to your true distribution because you will have an integral here, and you can drop into you can let them set in the exponential family. Your approximation distribution and true distribution is in the exponential family, then they will have you can write the integral, then you will have a distribution also in the exponential family, right? So using what kind of distribution depends on your problems. So here I'm using Gaussian distribution just as a simple example because Gaussian distribution only need to calculate the mean and variance. It's the two features of the Gaussian distribution. Oh.
And in this example, you can use the TB.
I just give examples because for EP algorithm we just to update each term and then iteratively update the second factor. Then we continue. So here I just want to give example. Maybe I can change the TA. The TB term may be just x. It's easy to integral. So only this part is not easy to integral. I just give example to show just we want to talk about when we want to update this term, the integral does not have the closed form solution. Because when we want to update this term, it can use the regular EP algorithm.
Okay, you mean the next step, you want to just calculate for the TBs.
Yes.
If the TAX is done,
yeah.
And
if
TA instead of the
yeah.
x2 plus 1, just put it the x.
Yeah.
Okay.
Just for TA term, I will do this process, and then for TB and and then continue.
Okay, and
then convert.
Okay. After these two steps, at the end of that, how can you use the both results of the TA and TB? Yeah, I mean the integral.
After you update the TA, actually we are interested to get the new approximation of Q of x, because we want to find Q of x to P of x. And we updated the TA of new, then we want to update TB, then TA of new actually goes into the Q naught B if we want to update the TB. So the T of the updated information goes into the Q naught B, right?
Okay.
So after convert, I got a question. If you got all of the approximation of factors, you just multiply them together to get the Q.
Oh.
Yeah.
Okay.
Actually, I guess how did they handle stuffs when you cannot do the division? For example, like when
You
the
mean
variance,
this division?
yeah, when the variance of that Gaussian of nu is smaller than the variance of that slash A. So in that case, how do I mean in the case that you end up with negative variance, how do they implement that in practice? Like, because you have this Q nu, you get projection, right?
Yeah.
You can be promised that this Q nu will have a variance kind of bigger than the Q dash A there. If the variance is smaller, then you will get a negative variance for the TA tilde nu. So, I mean, in practice, how do they implement that? Like in those cases, they just... It's okay, we can ask Sean later. You can ask Sean afterward, because I guess you didn't implement that, right? Yeah, okay.
Yeah.
Yeah, and I think, for example, the part, the variance is bigger than, for example, the Q not A. It's because it's the approximation of TA in terms of the other terms, and it shows, for example, in that estimation in that area, we have, for example, a less certainty to have the TA, and because of this, the variance start to be bigger and bigger, and it shows based on the others, this term, it's similar to, for example.
Well, actually, bigger and bigger is okay. I'm talking about the other way around. Is if you're after the projection, if the variance is smaller than your Q dash A at the beginning, then you will have you cannot do the last division there, right? Because then you end up with a negative variance. Then you need to kind of do something. I know they did something like in practice, but I just wonder, like, because I never implement that. I know Sean did, so we can ask him afterward.
And a point. I was just going to my question. So for the TA and TB, you have now you have 2z. Yeah. You just solve the integral. Okay.
Yeah.
So how can you just integrate in these 2z together?
Yeah, because the Z is nomination factor. Here I only write the TA new of term, and actually for TA approximation, TA of new tutor, it also has a normalization factor.
Okay.
And all of this normalization factor and the factors from the division of the two Gaussians, and they will combine together at the normalization factor of the T tutor of nu.
Okay. No, I mean the Z. You have the two Z's.
Yeah.
And you want to find
The Z also will go into the normalization factors of the TA of nu. For B, the Z for the TB and the different another
you have
normalization
two
factor
different.
goes into the as a normalization factor for TB tutor nu.
And the mean and variance is the mean and variance of P of x.
Which part?
In the right side, you have the mean and variance. This one is the mean and variance of the P of x.
Oh, no.
This one means a variance of
This
TA of
mean-
X.
This means just
Okay.
just this one.
Yeah, you have to
We just
be
we updated this term, and but this term is also old, but this part is new, and the mean variance of this Q.
you
And
update
we would we actually iteratively update the mean variance and mean variance of the
okay.
Q,
Okay.
and finally you can work a Gaussian Q.
Okay.
Yeah. Any questions?
So
Yeah, we move on to the power EP. The power EP is mainly works on the integral of this kind of the form. The beta can be any value you want, and in that case the P is equal to -1. And in order to give an intuitive explanation of the power EP, here I suppose that this integral about the TA is not easy to evaluate, but the TA of x1 over NA Q naught A dx is easy to evaluate. Here, the NA we consider is positive integer, but actually we only consider it a positive integer just to give an intuitive explanation of the power EP. Actually, it can be true any value you want. So it also means that beta is equal to 1 over NA. But just it's very intuitive way to explain power EP. So we choose 1 over NA. NA is a positive integer.
So you mean that just use the power EP just for the finding the easiest way for solving that
Yes.
problem? Okay.
Yes.
And if
Because at that time the EP drops down, so we cannot use EP
Yeah.
at that time.
okay,
So how you use this part to still solve this problem. So it's called power EP.
you mean you're using the PEP just depend on the TAX?
Oh no, it just
Because
I just give a big picture of the power EP. Suppose now we have two problems. The posterior distribution, it has two terms, and one term is not easy to evaluate, and this term is just easy evaluate. Okay, for power EP, how does it works? If I update these terms, okay, EP doesn't work. How do I update these terms? I'm using the power EP equation. Okay. When finish updating this term, I will update these terms. Then I will also using the power EP, but at this time the power EP will reduce. How to say? Will come back to the regular EP. It will have the. Do you know what I mean?
yeah.
So
You will assume the beta is equal to 1.
yes.
Yeah.
Since I consider now this term is easy to evaluate, then I can using the regular. I can write it in the regular key, right? The Q naught A is equal to the QX TA tutor x1 over NA factor. I consider this is the factor, and then the Q nu of x is a projection TA1 over NAQ dot A x dx. And the T So consider this part as a factor, so we can write this as in the regular equation. And if we define the FA is equal to TAX 1 over A, and FA tutor is equal to TA tutor FX TA. Actually, I can replace and substitute this definition into this equation. It's FA and FA tutor. And FA tutor new. Yeah. So at this time, why substitute this equation into this is totally same with the EP equation. But here we need to know that FA is just equal to the TA to 1 over NA. And from this equation we also can know that TA of X is equal to the product of total NA TA to 1 over A, right? So because TA 1 over A, I'm using FA to denote this. So actually it's equal to FA times FA times FA totally NA number.
YK is
For
equal
the
to
first equation,
all of them are the TA of X.
Yeah. Because in our posterior distribution is equal. Actually, we should do that. This is our object, our target. We want to do this integral, but it does not have the closed form solution. But we know that the TA to 1 over NA and times Q naught A and integral, they have the closed form solution. So I just actually factorize TA of X into the product of NA numbers of this factor. So now it's equal to the product of the NA number of FA. So according, this is standard EP. Yeah. Now from this equation we know that EP just to update it FA term step, and then we will update FA. So now we have the total NA number of FA. So we can call it, we have NA copies of FA, right? Because totally they are same. So EP will first update the first fraction factor FA, then we'll finish this iteration. Then we'll continue second iteration. Okay, EP will update the second factor of FA, and we'll continue the third and fourth until they finish all those factors. They finish the update of the TA of X. According to the standard of EP, they also can finish the problem and find the integral of the Q, this integral. But they have the problem is when the EP algorithm updates the second factor of FA, at this step, the first updated information will goes into the Q naught A. So the second approximation FA will use itself from the first update, right? So the third will use the information from second, because all of the FA are same. So actually, it means that for each update, it will the information of from itself. So it will produce a feedback loop. So it's not a good thing. And if the number of the NA will increase, so the time for convert will also increase. So it will decrease. It decreases the convert speed. So it's not. So we will use So how will the power EP works? The power EP also wants to update the F factor and got a FA new. After they got the approximation of this FA new, it will not update the second and third and fourth. No, they just copy the first update and replace the approximation to all these copies. So for the power EP, I will for the power EP, the first two slides are same. Okay, we still want to update the fraction factor at A, and we take the projection and got the Q nu of X, and the Q nu of X divided the Q naught A, we got the updated approximation for the FA nu, yeah. And now we want to do the copy. I want to replace this approximation to all the copies. So for all the copy, so for the updated new tutor, because we total have the any number of the copies. Yeah, here actually the FA tutor new, FA tutor new is different. Here I use a bar maybe to represent. It's different. And actually for the posterior, we only have one factor FA is updated. So here the old see here the old FA tutor. We also have total n numbers. Because we only have one factor updated, so we'll divide it 1, and this one is updated by the new, and this is the new equation, right? So here is a Q new divided Q naught A of X, right? So these two equations is equal. And from this equation, we can calculate the FA new is equal to right? And okay, this part is equal to okay, 1 minus 1 NA, right? And Q nu X Q naught A X. Right? The Q nu right now is equal to this. I will just copy this equation from this side. So I think to 1 over
have NA because the power volume is
NA. So now
It's 1 over NA.
here, yeah, 1 over NA. Right. Yeah, we got AAQFAU. Then here, yeah, oh. Okay. So after got here, I forgot. I want to just to change the notation because here we only updated the FA. So I want to use the Q prime to represent Q nu. So Q prime to represent Q nu. So it's okay. So after I got the approximation of FA nu, right now I want to find the Q nu. Because at that time, all of the NA copies is replaced by these approximations. So now the Q nu the Q nu is a Q, the previous Q of X, because all of the NA copies is updated by the new. So we will divide the FA X, these are old NA copies, by new NA copies. And then we Q of X. I move this part to this part. Fn AFX new divided AX NA. So actually this equation also can still be simplified. We can, we know that the Q naught A times F tutor A is equals to Q of X. So here we times Q F tutor of X F1 Q prime X. So here we times F tutor A, and we divided F tutor A and also times F tutor A and 1. Right? I multiply F tutor A and also divided F tutor A. And this part is equal to Q of X. So Q is equal to Q of X. And I can move the F tutor A outside. Okay, F A tutor outside. And this part equal to F A tutor 1. Yeah. So yeah, this is a simplified equation. Yeah, for this part. And from this equation, we can know that F A nu divided F tutor A is F A nu divided F tutor A is equal to this part, right? So we can substitute this equation into this equation. The Q of X is equal to Q of X A, so this part cancel, and this part cancel. Finally, is equal to Q prime of X. So you just to know that after this replication for all the copies, the Q new still equal to the Q prime of X. We did not change anything. So this is the power EP. So this is the power EP. Here I need to mention that for power EP here, the power EP actually updated all the fractional factors at the same time, and each factor is updated according to this equation. And we also can update each factor according to the standard EP equation. As just said now, we can update iteratively for each factor. So for standard EP, the approximation will not synchronized, but when it can work, it will have the same. It will be the same. All approximations will be the same, and it will have the same answer as the power EP. So this part and this approximation part for each fractional factor, and for the standard BP to update each fractional factor, they will have the same answer. So actually they have the proof to demonstrate that they are the same. But I will not talk about it today. Yeah, I think that's it. Yeah.